like 25 feet if I open 40, 55. If I don't do that, though, it kind of blurs. Okay. Yeah, thank you for telling me that now. Okay, so is this meromorphic? Now, what's the domain in question? So the zk is just equal to k, and let's say that the domain is the complexes, all right? Certainly the positive integers, which everyone knows are the natural numbers, are, they're isolated, right? I just
Why is 0 not a natural number?
Because everyone knows that 0 is not a natural number. Only a crazy person would say that 0 is not a natural number. Yeah. I don't. For me, n includes 1. Okay, so yeah, I mean, definitely that definitely reproduces the poles, right? And if you look at this minus the sum of the, minus, if you look at that minus, zk, it's definitely analytic at each one of those. But there's a problem here, right? What happens if you look at the naive thing at 0? What do you get? Oops. So apparently this function is not analytic, right, at 0. So what do you do? Simple enough, you just add infinity. So f of z, what you do is you just do sum k equals 1 to infinity, 1 over z minus k plus 1 over k. And there you go. Now we have f of 0 is equal to 0. And if you look at the difference of this function with the prescribed poles, it is indeed analytic on the natural numbers. The difference of, this function and the pk. Now, Gamelin proves, in fact, that this converges. In fact, this is, meromorphic. He proves that this is meromorphic on the prescribed set, and he proves it's a uniformly convergent sequence of functions on page 348 to 349. This is kind of a typical song and dance here for this Mittag-Leffler thing. Whatever the prescribed bunch of infinities that you want, you just basically take the sum of those principal parts as your naive guess, and then if you're clever enough, you can subtract off the infinity by just subtracting off the piece which becomes infinite at some offending point. At least that's the examples I have in the notes. I don't know what generally happens. Not, What was that? What was that? That was not a normal beep. That's a better beep. Mm. Oh, come on. All right, fine.
Stand on top of the chair and hold it down.
Well, yeah. Before we had these new improved screens, we used to be able to do that. Well. It still thinks. How does that still have power? Here, survive that, sucker. Come back from that one. Oh, yeah, it's whatever. All right. I am, as you can see, I have had IT training. I am doing what professional IT people do when solving a problem here. All right, so the other example, the next example is if you have a lattice of singularities. right? So what's a lattice look like? Hopefully it will come back to us. So you might have something like and so forth and so on. Maybe this is omega 1, this is omega 2, something like that, or vice versa. And so a typical thing in here is something like m omega 1 plus n omega 2. So you could have this, you could actually prescribe this lattice of singular points. Suppose that there's a double pole at each one of these, all right? And the function which reproduces these and is meromorphic, reproducing this lattice of double poles, is known as the Weierstrass P function, I think, which I would love to project and show you the formula of sometime this year.
You tried turning it off and turning it on again?
That's what I was.
That was the other
That. Oh, I'm sorry. I'll get there. It's right now the red circle. All right. So very exciting this is. Anyway, so golly, I tell you, with all the lousy days. Just hand my computer around. It's funny. Come on. Okay, so past the Weierstrass example, we have this example, pi squared over sine squared pi z is equal to a sum k equals minus infinity to infinity of 1 over z minus k quantity squared. This is from page 169 in my notes. So what you're looking at is this is a partial fractions decomposition of this function, right? This is now, at first glance, that would seem to contradict something we proved earlier, which was what? What did we prove about meromorphic function? Every meromorphic function on the extended complex plane is what? A rational function, that's right. Isn't this meromorphic on the extended complex plane? I mean, it's not a rational. First, it's not a rational function, right? It's definitely meromorphic on the complex plane, right? Every singularity it has is isolated. The isolated singularities happen at the zeros of sine of pi z. The zeros of sine of pi z are precisely the integers, right? K equals 0, plus or minus 1, plus or minus 2, so forth and so on. But the rub is, if you look at this, it has an essential singularity at infinity. So in fact, this is not meromorphic on the extended complex plane, even though it is meromorphic on the complex plane. And so that's why it's not a contradiction to the theorem we proved the other day about rational functions being meromorphic. Now, Gamelin proves, in fact, that this series of functions is uniformly convergent. That means you can do calculus on it. What happens if you integrate this? Can you integrate this? Can you integrate, what is it, cosecant squared? What's the integral of cosecant squared? Good grief. It is minus cotangent, right? I'm not sure about the, are we sure about the minus? I think the minus is right, yeah.
Shouldn't there be a pi squared on the
Pi squared? Oh yeah, but I just said this, right? Okay, fine, you want me to put the pi squared out here? You might, I mean, if I'm after that, then I'll agree with you. So it just becomes that then, right? You know what? I think I can still make do with this. It's not ideal, but maybe it'll work. Let's try it out. I'm just now realizing I should have my own projector.
Just projecting it as Dr. Wayne style.
Dr. Wayne style, which is just like on that.
Yeah.
Yeah, I'm getting there. Come on. My computer needs the juice. There we go. Okay, so on the one hand, you can integrate the you can integrate the 1 over sine squared pi z, right? But on the flip side, you can integrate the series. And what will that give you? That will give you another series, right? In fact, another Laurent series, I think, right? Where are we? So there's the Weierstrass P function I mentioned. Oh. Hey, actually there's, oh man, if I could always do this, I could write on my notes.
Yeah.
This would be better. Ooh. Oh man, but this is only when it breaks. How can I always break it?
Unplug it.
Well,
yeah.
then you go full Dr. Wayne mode and you lift it up.
Lift it.
Unplugging it might work.
Unplugging it, huh? All right, so here's the calculation I'm referring to here. So on the one hand, we integrated and we got the pi cotangent pi z. On the other hand, if you integrate this term by term, you end up with this thing, which when you rearrange and do some sneaky rearranging of terms, you end up with this expression pi cotangent pi z is 1 over z plus 2z sum k equals 0 to infinity of z squared minus k squared. And that is another example of MittagLeffler. We integrated one MittagLeffler result and we got another, basically. And when I say a MittagLeffler result, I mean some kind of like infinite partial fractions decomposition for a given function. That's kind of the idea. That brings us to the next topic, if I can, which is that of infinite products. So the infinite product right here, really, the sum j equals, the product j equals 1 to infinity of p sub j is the exponential of the sum of the logarithms of p sub j, provided what? The condition that be defined that way is a little bit quirky. You need that only here's some fine print. If finitely many of the products are 0, then you define the infinite product to be 0. All right. If infinitely many of the products are 0, then I think it's said to diverge to 0. Something like that. I don't know. The convergence and the divergence here is a little bit, I'm still grappling with it myself personally. But anyway, the infinite product converges only if the products converge to 1 and if that log converges. Now, I mean, this expression can still be understood in the case that the logarithm goes to minus infinity. If the sum of the logs goes to minus infinity, the infinite product is understood to be 0. I would say it diverges to 0. Okay. On the other hand, if the product converges, then you can also write that the infinite product is the limit as n goes to infinity of the partial products. Very, very much. That's a very satisfying thing, right? I mean, that's just kind of like what we learned before for sums. There is, in fact, a theory of convergence and divergence for products, just like sums. Don't worry, I'm not going to hold you responsible for that because we don't have time, and I don't think I have enough examples yet to teach it properly. So, but just a sample, a sample example or two here. I think we might want to hit the lights in the back in this case. That might help. Yeah, I think that'll help. What do you think, Sharon?
I agree.
Okay, so first of all, suppose the 42nd one's 0 and the rest of them are 1. Then the product is 0. Okay, that's part of the definition. Here's a more interesting one. This could be a Math 200 question. Suppose you have the p sub j is 1 minus 1 over j squared for j greater than or equal to 2. Calculate the product of, 1 minus 1/4 times 1 minus 1/9 times 1 minus 1/16 times 1 minus 1/25 times 1 minus, you get the idea. So it's like this times that times that. You see what happens is there's some cancellation here, right? It cancels down to 5/8, which is 1/2 times 1/4. And if you study the product, eventually you'll see this pattern that the sum j equals 2 to n, the nth partial product is actually 1/2 times 1 plus 1 over n. So as n goes to infinity, the product goes to 1/2, right. And you can prove that with induction. Another example, if you have the product j equals 2 to infinity of 1 over 1 minus j, well, here we have 1 over 1 minus j going to 1, so that's kind of like analogous. What's wrong with me? Analogous. If you have a sum over a sub n, if it goes from 0 to infinity, we know that the nth term test is that if it diverges, if a sub n does not go to 0, it diverges, right? If it does go to 0, it doesn't give you that it converges. It just says it might converge. In the same way here, if the product goes to 1, it might converge, it might not. This one has a product which goes to 1, and even so, it's divergent because the sum j equals 2 to infinity of the logarithm of 1 over 1 minus j is in fact minus infinity. And so this is an example of a product which quote unquote diverges to 0 in that sense. Here's another example. Come on, go down. Why won't it go down? I don't know how to get to that. Stupid thing is too smart for me. How do I get that? I need too many options. Enable scrolling, perhaps. Yay, okay, scrolling. So this product is kind of just like the last one, but now alternating, and that's just what it takes to do the trick. When you change it to alternating, then you end up with it converging to 1 as it happens. All right, so there's a theory of absolute convergence. You can talk about products of functions being uniformly convergent to their product, and a lot of the usual things kind of go through again. So the really interesting thing then is to discuss the connection between the MittagLeffler and the product. All right, MittagLeffler is something about an infinite sum. Now we're talking about infinite products. What's the connection between these two things? Is there a connection? There is, in fact. So here's the finite case. If I have a product g1, g2, gm, right? And if I look at g prime divided by g, do you see why it's this? Think about g prime. Think about the n-fold product rule. It's like g1 prime, g2, g3, gn, right? Plus g1, g2 prime, g3, n. And each one of the n summands in the n-fold product rule, you have just one derivative, and the rest are just as they are. So when you divide by the total product of the n things, everything cancels out except for the derivative divided by the same function. In other words, g1 prime over g, these are just the m terms, I should say, in the product. They're coming from dividing the m-fold product rule. It's the product of m things. Anyway, do you see this? I mean, we can all derive this in the finite case without too much trouble. If you want to, we could do an inductive proof. It wouldn't be much work. The cool thing is this extends to the case of infinite products and sums in the following sense. If you have these functions analytic on a domain D such the product is converging normally, which means that it converges uniformly on compact subsets of D, just like that notion of normal convergence we talked about before for sums of functions. Well, okay, so in that case, then the product function G of Z, its derivative divided by the product is equal to the sum, k equals infinity, 1 to infinity, of the derivative of the product of the functions which are forming the product divided by themselves. That, I mean, to me, this is some kind of dark magic. I mean, it's just really cool. And so that brings us to this so-called Weierstrass product theorem. The Weierstrass product theorem states the following. It says if you have a domain in the complex plane and you have some sequence of distinct points, all right, no accumulation points, kind of like the sequence we were looking at today to start with for MittagLeffler. And then if you have a sequence of integers, positive or negative, you can find a meromorphic function whose only zeros and poles are the points ck. So now, at the start of today, we could prescribe poles, right? This is saying you can prescribe a set of zeros and poles at a given sequence of isolated points. Pretty awesome. And you can match the orders of the poles and the singularities. This is very, very greedy theorem. Let me show you how it works. The proof is on page 358 to 359 of Gamelin, of course. For example, this product of functions, here's one. Product k equals 1 to infinity of 1 minus z squared over k squared. Where would this have zeros? It has zeros at z equals to plus or minus k, right? And those are, I think those are those double zeros? Let's see here. Excuse me. So the g sub k is 1 minus z squared over k squared, right? If you set that equal to 0, what do you get? You get, I think you get zeros at plus and minus k. I think they're simple zeros, actually. Yeah. All right, well, that's not that exciting of an example. That's just an example of an infinite product. That's not really what I'm after. This one, oops. Oh. This one needs a factor out front in order to converge. So it's like this would have zeros where these functions, 1 plus z over k would have 0 at z equals to minus k, right? So here my sequence would just be, I suppose, like the negative integers, like -1, -2, -3, -4, so forth, right? But you can't just use this alone. You need this in order, that factor is needed in order to make this product converge, is the point of this example. And the analysis here is somewhat delicate, right? But let me go on here. All right, so come on. This is something I wanted to read for you guys. I skipped over it somehow. It was on page 172. Where did it go? There's a simple argument I wanted to share with you guys. I'm sorry, I can't find it. Oh. I found it. Come on, I'll get to it eventually. So what I wanted to talk about was the intuition for the convergence factor I was just talking about, all right? So the convergence factor, this one has no convergence factor. It's just basically this thing gives you the zeros that we're looking for, right? There's no, the next one had an exponential that was forming the convergence factor. So this argument here is very, very, very nice though. Suppose you have, just follow me along here. Suppose you have two entire functions, f of z and g of z, all right? So this f of z and this g of z, they're entire, all right? So like, holomorphic on C, all right? And they have some zeros, but suppose they share the same zeros up to multiplicity, right? What does that mean if you divide them? Think about dividing two functions that have the same zeros. The z, right? They basically have removable singularity, right? Yeah. So like every place where you have a zero, you have z minus say zk to the m. For f, you also have z minus zk to the m for g. F over g, the zeros cancel out, and you're left with a function which is again entire, right? So f over g is naturally identified with an entire function which has no zeros. That means then that if you let h of z be the logarithm of f of z over g of z, you can do that, right? Because f of g over g, f over big G is non-zero on the complex plane, so I certainly can take its logarithm everywhere, right? And so h is an entire function, and then if that's the case, then you can just exponentiate this to get that f of z is equal to e to the hz times g of z, right? So what this means is that if I have, basically this is going to be the, if I have two different functions which have the same zeros on the complex plane, then there's got to be some sort of exponential function like e to the hz which relates the two. Just that's their relation. And you see that at play down in this example. Not this one so much, but the 4.3. I think that, oh man, come on. Sorry, guys. I think that's the significance of this thing here. Anyway, let me go on. All right, so here's an example which actually has a little bit more to it. So I'm getting used to this new board. Consider G is the sine of pi z, and f of z is z times this infinite product. All right? Now, both f and g are known to be entire functions, because that product was studied in an earlier example and was shown to be entire, all right? And they have the same zeros. They're both 0 on the integers. So here's two entire functions. They match. They have the same zeros. Each 0 is simple, right? Simple zeros on the integers. And so you can try to relate them. So like, well, we can derive the e to the hc that we derived from general principles up here by basically sorting through the relation between the product and infinite sum. Let's see how that goes. So let's see. So the derivative of the logarithm of f, right? So if you take the logarithm, the derivative of the logarithm would be f prime over f, right? So this infinite product differentiated divided by f, but that theorem we had, right, says that becomes this sum, right? And but this is whoa. this is that, which we have previously worked out from the integration of the 1 over sine squared is pi cotangent pi z. And then, so you have this from the term-by-term calculus, you can integrate this and integrate that, and you get this equals that. And so by the definition of the infinite product, you get sine of pi z, and then, but you know that sine pi z over z limits to pi as z goes to 0, right? And as this goes to 0, you've got, on the one hand, 0, divide by z, right? Then divide this by z, take z, limit z goes to 0. As z goes to 0 over here, you get 1 times e to the c2. On the other side, you get pi, so it follows that e to the c2 is equal to pi. So, I mean, these are the kinds of calculations you can do with infinite products and infinite sums. I just wanted to make you aware that there's this world of infinite products that you can calculate in. You know, we should obviously spend a couple weeks to really get good at it. I've given you a token problem or two in your quiz to work out. And if you search the archives, you'll find solutions to those. I just really wanted you to be exposed to it. It's not something I'm going to put on the test. I haven't done enough. When I taught this last time, I spent about 2 weeks on it. So, all right. Now, that said, I think what I'm about to show you, I'm more likely to test on because it's a little bit more related to residues. Can you hit the lights? Your eyes. So this is linked Infinite Series in the Residue by Noah Hughes. He was a student of my brother, and his paper is great for my purposes. Oh, hit the lights again. Sorry. That'll have to do. So basically what he shows in this little paper is that you can calculate residues in a certain way to calculate a series. Let me show you what I mean. So it's all based on, oh, come on, this stupid thing. Yeah, hey, go away. Are you going to load? Okay. I did hit open. Let's try it again. Okay, now it's just messing with me. Come on. Stupid thing. It's very frustrating. Like, usually a PDF just opens, right? Like, what on earth? Well, that's not it. This ain't it. Not it. Not it. Fine. It's thinking. I think you're right. I've somehow got it opening about 5 of them. But, I mean, no, it is not. All right. Ultimately, if technology had been my friend today, we would have had the 10 minutes we needed to understand this together. I'm sorry we didn't.
See, technology is just resentful that you keep dissing like 0 being an actual number.
Yeah.
Like, not admitting
Yeah, I think it says nothing.
Technology knows
I think this has nothing to do with your misunderstanding of the notation n. But so ultimately the result is this. If you want to sum n equals minus infinity to infinity of f of n, all right, given these preconditions, all right, f has to be analytic on C except for some finite set of isolated singularities, all right? And it has to be, well, okay, anyway, there's some fine print here. Anyway, it is equal to minus the sum of the residues of pi cotangent z, f of z at f's poles. I know that doesn't seem like much, but that connects the sum of a, you know, that's just a, like an ordinary series, right? A sum of numbers to the calculation of the residue of cotangent times f. And this turns out to be very, very useful to calculate certain, like for example, you can show, you remember the p equals 2 series? It sums to what? Pi squared over 6, right? Here's a proof. Sum n equals 1 to infinity. 1 over n squared is pi squared over 6. You look at 1 over z squared cotangent z. You find its poles, calculate its residues, add them up, out pops pi squared over 6. That's kind of cool. The other way to derive this is with like Fourier analysis. So anyway, I'll try to talk more about this probably Monday after break, but I wanted to get you started. I think I have one problem. Don't forget that this PDF is linked, and it's very easy to follow. It's pretty well written. It's just a student who wrote it, so he's like right where you guys are. He just read a chapter in a book and put this together. So it's pretty good. Thanks, guys. Have a good break.